Good afternoon to those of you in the East and good morning in the West. So thanks for coming along today. What I'd like to do over the next approximate hour is to go through the status of the use of expressions in Fluent, and then hopefully we'll also have some time to have a go at showing you how easy it is to bring things across from CFX and then modify the expressions as needed. So without any more ado, I will start going through a short presentation that will set the scene. So this is the plan for the presentation. We're going to go through some motivation for learning expressions, showing you how you can adopt them, and then we'll go through the basic syntaxes, uses of the editor and manager. We'll do an example, and then we'll also look at plotting expressions and using expressions in reports, and then we'll try and have a look at a little live demo. So the key idea of expressions is we want to make things easy. We want to make things easy to check, and we want to give the flexibility that is available in CFX and was available in AIM to Fluent users. So an expression is something that can vary in space, in time. We can use iteration in it to help us ramp things in or change things. And we can obviously make use of solution variables, various constants, functions, even profile data can be brought in and used. So anywhere where there's profiles or parameters pretty well in Fluent, you can now start using expressions. And the syntax is very similar to CFX or AIM, only they've been extended greatly. And you'll see here, this is a standard T-mixer. This is an expression, how it appears in the GUI for the inlet velocity. Whenever an expression's in use, you'll see this little f of x symbol here. And that basically says this is an expression entry here. So let's have a look at how this compares with what we would be doing without that in Fluent. So if we want to set a sinusoidal pressure at the outlet for a transient simulation here in Fluent with these parameters, so it's basically a constant plus a sinusoidal variation about that, then with a UDF, you have to go in and set up a C or C++. You need to declare your variables, declare your pointers. Then you have to know some commands to get things like the time. Then you can set pressure with an expression. Now you have to loop over all of the positions in the thread which covers the face of interest and set the pressure up. And then you close out of that. Now, at this stage, you're not able to visualize anything or check anything, so you have to do that once you start running. Of course, if there's any compilation errors in that, you'll only know when you try and load the UDF. Now, what happens if we do this within Ansys Fluent now with expressions? Well, we can make a couple of expressions here. P0 is our constant. Here is our varying expression for the pressure. We can stick it into our entry in the panel here. We get a little f of x show up. No, we're using it. And we've already run. So this has all been done without a UDF. The nice thing about this is there's a lot of diagnostics we can do on the way. We can actually plot this as a function of time before we even start to make sure that all our units and things have come together. Also, we can make sure that we're we've got consistent units and things, which if we just go back to that UDF, it's up to us to make sure this is all giving us units that are in the SI system. So you'll notice that the atmospheric pressure has to be spelled out here, whereas in the expression here, that we can just use atmosphere and let it get truncated. Sorry, not translated. I didn't mean truncated, translated automatically. So at the moment, we can use them in boundary conditions, source terms, some material properties, not all because some are quite complex to set, post-processing, and reporting. And the list is growing here with each release that we have. We can now use them for patching in start. And then the nice thing is that once we've got an expression, if that resolves to a field, then we can instantly plot it, and I'll show you that later. We do not have to create a new variable or use defined memory or anything. It's a direct feature. So let's start going through this. I'll assume that you're new to expressions, so I'll go through the basics so that everybody on the webinar will get to see the basics. There's lots of documentation online now. So the first thing to know is that these are written in a Python syntax. And with that comes an enormous amount of power. It actually means we can do lots of things here that we can't do in CFX. And I'll show some of those in a moment. They are case sensitive. So just like any language. Now, we can also distinguish between values and quantities. So values are just our numbers or our basics. So a number, a real number, an integer, or a true or false for a Boolean. As soon as we get quantities, these become a real number that has units attached to it. And those units go with it. So when it goes into an operation, the units are subjected to that same operation. So if I square a quantity, I'm going to end up here with kilograms squared seconds to the -2, plus that large number squared at the front. We can have expressions that return a single value. So we've got a few examples here. So Vmax here is a function of only time. The inlet velocity here is a function of some given flow rate in US units with an area for flow calculated directly from a function here. So we don't actually have to go and measure that separately. Here we've got a source term of heat, and we've got an if statement. So if the mass flow average of the temperature on the outlet is less than 120 C, then the power is this, else it's nothing. They can also be multi-valued. So obviously we need that if we're going to set a boundary condition on a face that's, say, a parabolic flow, then we need to have things which are a function of, could be multiple variables, could be a couple of space variables and time. So we can have a time varying, spatially dependent inlet velocity. Most things are just the variable, but we know as soon as we get into slightly more complex simulations, we might have to have some qualifications on variables. So if we have a multi-species setup, then we're going to have to be able to tell it if we want the mass flow of a certain species, then we've got to be able to tell it what species, or if we want a mass fraction here. So we can say this mass fraction can have a context, and the context here is that it's of species CO2, but it's also got a second context here. It's from phase smoke. So we must have at least 2 phases in this. Or we could have just a single phase as a context here. So in the velocity magnitude is just a depending on which phase we're in. Say we're either in the liquid or we could be in the smoke phase. The same sort of smarts that are in CFX are all in Fluent to help check. So that means that, for example, if you put in an expression which has got the wrong units, it's going to tell you what's wrong and what's required. So here, clearly somebody has tried to put in an absolute mass source when it needs the volumetric. So you need to divide it by the volume, and now it has the correct units. So that will always be flagged up. Some general things on units here. So we've got all of the typical multipliers, all the way up from nano to giga there. You use a caret symbol for a power, and when you divide, you've got the choice here of meters/seconds or seconds to the -1. That's entirely up to you. You can have multiple groups here, so you can have all the fundamental units here, or you can have a mixture of things like watts. When you do multiplications of numbers and things, the units get consistently carried through. You may find that the units come out in some kilogram meter second set of powers when you might have expected it in something simpler. But you can always check that the translation is okay. It automatically checks for consistency. It automatically converts, and I think this is a nice thing, that if by chance you've got data in some strange units or pressures in atmospheres or temperatures in sea, you can actually use those inputs and let the internal database in the code actually do the conversion for you. So what that means is that you no longer have to worry about doing any of this in a spreadsheet, and we know that that is terribly, terribly error prone to do things like that. Here's some common units. So you'll be able to get a recording of this this webinar at the end, those who've attended. So you can have a look at this, and we can even post these slides. So, you know, it's got a very wide range of units you can do. And again, if you're in the appliance business, you might be getting data in BTUs or something. Don't know what they are even these days, but you know you want to convert them, so you can just stick those numbers in. Now, there's a couple of ways of using expressions. So wherever an expression is available, you can actually type it directly in the panel. Now, I'm not a fan of that approach for a number of reasons. Firstly, they get scattered throughout your setup. And if you want to reuse them somewhere, you've got to go and dig them out. You can't export them from all these individual panels. So by far, I think the best way of using expressions is to use the expression editor, and then when you come to actually use an expression somewhere here, so this velocity is going to be changed to an expression, you can put a new expression, but also any existing expression that reduces to the correct units will show up in the list. So all I would have to do is click on VIN here, and it would automatically jump into the list. So if I were you, I would try and consolidate all my expressions in this expression editor, and we'll see some reasons more for doing that a bit later. When we use this expression editor, the nice thing is it provides us with a large window to work in. It provides us with color coding as we generate, and also a lot of feedback. We can also put in things like a comment so that we can describe what it is. So if, for example, you've taken data from a paper, you might want to put the ref in there so you know that if you ever want to go back to where you found it from or the website, you can put in there. The other thing is if you work here, you've got a lot more space to have these function panels, and there's a whole load of panels that can come up, and then we can choose the type of function, and then we've got these drop downs. So although we can type things in here, lazy is good because this will give you the correct spelling and syntax. If you type it in yourself and you get the spelling wrong, you'll know because it will flag it up as not being valid, but you'll have to figure out what you've done wrong. So for example, here, we want to calculate T average at the outlet. So we've gone down here to do mass flow average, and it's populated that. Now we can click on that expression there, go down to temperature, choose static temperature, and it will fill it in that box. You can see this has got a red frame around it. That says that we're still inputting an expression, and at the moment it's not valid. So if we give up at this point, we don't have a valid expression. So the syntax highlighting is really nice because once we know that this is valid, it will come up, you know, in this pinky mauve, and then we'll get other things. We'll get greens and blues, etc., showing things. Here's a few commonly used functions. So things like area average, area integral, mass flow average, volume integral. One thing that you will see here immediately that's different from CFX is that this location would have been something where you would have said at, say, inlet, and that was it. You could only do it at inlet. If you wanted to do something over multiple surfaces, then you had to create combined surfaces. Here, this can essentially be a Python list in here. So we can have as many as we want, and it will then use the inputs from those to be the surfaces over which it works. So again, here we've got to that square bracket. We've clicked inside there. We can go out to either boundary zones or surfaces. So if we want 2D input, or cell zones if we want three-dimensional input, and then the location selector will pop up. We've got all the tools here. So if we wanted to choose both inlets, I could hit the X to get rid of this, pick the two inlets and insert. And now once you've got this set up correctly, you've got a blue for the variable and a green for a valid region. So this is now set, ready to go. You can also do things here by starting to type yourself, and it brings up then a list of things that you could use. As you type more, this list will reduce. But what it will not bring for you is any bracket structures. So I now need, if I want to put a bracket in, I can hit T here, and I can wait until I find, for example, the variable I want. Like it can be T for temperature, it's short form, or it might be some other variable that I want here, like turbulence dissipation rate. And then I can go through and I can put my square bracket in to determine my location and type it. If I hit this button here, if it's possible, it will calculate and tell me what the current value is. So that's also a nice sanity check as we set expressions up. There's a few other little things here which are useful. So once you've got this in and it's got the syntax all laid out, we can put a description, as I mentioned. it will tell us where it's being used. So if this is empty, you've created an expression and forgotten to use it. We can also use expressions for parametric studies where this can be driven as an input parameter or an output parameter. So that gives us the flexibility of using those. When we've got something which has got a variable in it, we can, for example, want to have a look and see what this time varying velocity is doing here. We can actually choose our independent variable. And if we've got more than one, we can set constant values for some of the others. And then we can choose the number of points in the range and plot. Now, one of the benefits of this expression architecture going into Fluent is now, if you go to any material that's got, for example, a specific heat set up, either through the standard NASA polynomials or through your own piecewise list or your own polynomial, they get plotted automatically for you. So it's much, much easier now to find those type of issues where previously you might have a heat capacity, for example, that could drift into the negative at a certain point of the range because you had a coefficient wrong. That will show up immediately now and flag that up. So there's been a really useful benefit from that. So what can we do with these? So the usual operators there, two stars for exponentialization. We've got the usual set of logical operators here. We can have conditionals, so we can have an if, and then we can have an and, an or, a not, an XOR. To do conditionals, we can have the full set of hyperbolic functions, mathematical functions here. So these are your things like your absolute values, your C-like functions where you can find the ceiling above something or the floor below a number. You've got some logs, some max and mins. Mod, so we can do modular arithmetic. We can round something, square roots, truncate it. We've got the standard trig. So all of these so far are not particularly new, but this is the exciting one as well. We can work with vectors. So no longer when we're doing things and want to create a vector, do we have to do everything with components. Or if we've got a vector and we want its magnitude, we can directly get that. So we can do dot and cross products. We can get the direction of a vector. We can get the absolute value later on, the magnitude. We can set up a vector as 3 expressions, where in this we would give each separate units. Or if we've got a common unit, we can use this for entry option, where we give the 3 components of the vector and then the common unit. Or we can give a unit vector. So we'll see some examples of that in the demo. We've got the usual type of variables that we want to do. So we've got things like current time, time step size, current iteration. And then we've got a whole load of variables where we can actually go in here and use a variable which you can either use this short form or its full form. So position is a vector with the 3 components you'd expect. So is velocity, but we can use X, Y, Z, U, V, W. And then things like time and that have a simple abbreviation, iteration, temperature, pressure, mass fraction, etc. So it's easy to grab stuff in. You've got a lot of stuff here as well. So even things like all the face areas and variables that you might want to get in here to work with, you can get in. You've got a standard list of scientific constants. So the usual set that you might want for setting anything up in your expressions. So let's quickly have a look at an example here. If we want to do a 1/7 power law for turbulence, then we can go ahead and do that. So we can go in here and say a new expression. We can set our U max. We can set our R, our radial component, which is the square root of x squared plus z squared on this particular inlet. There. We can give its maximum value. Although when you do the maximum radius here, we could actually have been smarter and done the maximum value of say, x on that face. And so we wouldn't need to change this number if the pipe diameter changed. Then we can also then actually construct the expression. And then when we want to set the velocity here, you'll see that both Umax and the inlet velocity that we've created show up. So we can just choose the one at the bottom and it will automatically load. And then this is what we'll get. So once we've initialized as well, we can go down and plot this in the actual geometry, not just the expression, but also plot the velocity and make sure, it's sitting there. At the moment, these are not coordinate system based like in CFX, but that's coming. So having much more flexibility with local coordinate systems is definitely on its way. So here's a few useful ones that are going to come up time and time again. Being able to compute the area, and you'll notice if it's a whole load of things at once, a volume, a heat source. What else is particularly interested in here? Area weighted average over multiple faces all in one go. Conditionals. And then we've got a couple of different velocity profiles here that we've set up. So when we're doing this, we're typically creating them here and getting a list of them formed as we work our way down. So we'd like to be able to manage that. And so there's some tools in here that we can use to manage our name selections. So we can click on there and bring up a manager. And so once we've got that, we've got all sorts of things pop up here. We can select an expression and get its details, so that's what it is. There's no description of this one entered. It's not an input or output parameter. It's a real. It's a single value. It's not a constant. It's not constant. It's not constant value there. It's used in inlet 1. If we hit compute at the bottom of this, out into the console will pop a little evaluation of this. If we pick multiple ones, it will actually do multiple computes and list them. Yeah, here we go. So we can get listings here and get this into a list and have a look and see what each is. We can do things here with the usual selectors to select things if we want to do that, if we want to list them, or if we want to copy one or whatever. There's also an important pair of tools here, which reciprocal tools. So what that allows us to do is to import and export. So we've got those two options, import from file, export to file. It's a tab separated file. So what that gives us is along the top row, we've got a description of whether the various components of the file, and then the various bits of it. So a name, definition, a description if it exists. If not, a parameter ID, a parameter name, whether it's an input parameter or an output parameter. So we've got that format there, and they're just tabs in between. So we can actually go and edit in here if we want, and then re-import, but just be careful to make sure you keep your quotation marks balanced. Things can be copied to clipboard and then paste into another session. So you can do a copy to clipboard, and then you can paste it into another session of Fluent that's open. So that just is a one-off paste. The other gives you a file that you've got for reference. Now, once you've got an expression that resolves to a field as opposed to just a number, you will see that under our tab of selections, the very first one now is expression. So as soon as you've got an expression, you can plot it. So this is called local temperature deviation. And what it is the temperature minus the mass flow average of the temperature at the outlet. So you could think of this as your variation about the mean. And you can now identify where you've got an excess temperature and where you haven't, and what the range of values are. So it's great that you can plot these directly. No need to create any user-defined memories or anything. They're basically available in the list, evaluated on demand, and you can straight away have a look and see what the results are. So if we can do this with them, we can also obviously do reductions of these we've seen. So that means we can also monitor them in expressions. Sorry, in reports. So we can monitor reports that are an expression. So we can go in and directly do a report definition. Now there's all sorts of predefined ones that are really useful, but if we want to do one which is our own particular expression, we click on expression, we can choose one from the expression editor, the list, and in it will go into the report, and we can start then monitoring it straight away. So you don't have to create them via this surface report or volume report functionality. You can have them already created in an expression, and then use them straight away as a report. For those of you who write TUI scripts, then how do we do that? We can actually use an expression in there, either, for example, by putting the full thing in, or just the name and doing it in quotes. So we can create these at the beginning of a script. We can also read in a file. So if we've got a file of standard expressions that we want to use across our scripts, we don't need to use TUI commands to create every one of those expressions each time. We can actually have a file with them in, import that file into Fluent, and then whenever we want them, we just address them as needed in boundary conditions and things. So what's going on here? Well, we have this very powerful expression language based on Python, which is now possible to do quite a lot of things with in Fluent. So it's very powerful for setting up boundary conditions, sources, post-processing, etc. And it's not as fully implemented as CFX yet. So we can't do everything that you could do in CFX in terms of places to use expressions. In terms of the capability of expressions, I think we've exceeded that because we've got vectors. I only showed you the most commonly used functions in that. But if you're an acoustics person thinking, oh, but I use the Bessel function in CFX, well, actually, you can use that in Fluent as well. So why am I doing this webinar? Well, firstly, I realized that there were quite a lot of people who weren't so familiar with the expressions, and I ran a few in-house ones for companies, and they found it very beneficial. But the other reason is that I'm really promoting now transferring your work from CFX to Fluent. There are so many benefits in terms of new models, numerics, parallelization, workflows, particularly with the meshing templates and how you can just flow through the workflow, that if you're a CFX user and you're not using really advanced turbo, and I mean advanced turbo, I don't mean doing a fan. I mean, if you're using anything like a blade row model, then yes, stay with CFX. But if not, it's definitely time to be thinking about moving your models to Fluent to get some of the benefits. And we're always happy to talk to you. You can raise it with support. You can contact me directly, and we'll help you with that process.